All right, welcome to The Explainer. I am so incredibly thrilled you're tuning in today because we're diving into one of the most elegant, powerful, and honestly frequently misunderstood mechanisms in all of science. We're going to set up a virtual field test to really look at nature's engineering nodes. So if you've ever found yourself wondering how life actually adapts to harsh conditions, without having an instruction manual or a blueprint to follow, well, you are exactly in the right place. Let's get into it.
So I want to kick things off with a pretty massive question. I want you to imagine a perfectly stable ecosystem. Everything's humming along, and then, bam, a sudden, immediate ecological change hits. Maybe the temperature just plummets, or perhaps the local foliage completely changes color over a short period. What actually happens to the organisms living there? See, the really common misconception here is that the animals somehow know they need to adapt, that they make a conscious choice to solve the problem so they can survive. But the truth is, life doesn't decide. It reacts.
Okay, moving to Section 1, the environmental field test. Let's boot up the digital simulation.
To really wrap our heads around this, let's run our own little digital simulation to see exactly how individual traits influence the survival of a whole species in real time. Picture this. Step 1, we start with a super diverse population of beetles. They're crawling around in varying shades of green and brown. Now, Step 2, we introduce our environmental pressure. We trigger a sudden shift in the ecosystem that causes the lush, green broadleaf plants to completely dry out. So suddenly, the environment turns brown. Step 3 is where the magic, or really the math, happens. The brown beetles now blend right in, while the green ones, they stick out like a sore thumb to predators. The new color of the environment is literally acting as a passive filter. And finally, by Step 4, over several generations, those camouflaged brown variants are the ones securing much higher survival and reproduction rates. When the dust settles on our simulation, the mathematical shift is just staggering. By generation 5, a massive 85% of the surviving population carries the camouflage trait, while only 15% retains the non-camouflage trait. I mean, the whole population has fundamentally transformed. And it's not because the green beetles decided, hey, I need to turn brown. It's simply because the environment stopped the green beetles from passing on their traits.
Which brings us to Section 2, Nature's Unconscious Filter. This is how survival actually works.
Here is the absolute crucial point you've got to take away from this. Natural selection is a passive environmental filter. I can't stress that enough. It is not an active, conscious choice made by the organism. The organisms that just so happen to be equipped with optimal traits will simply outcompete their rivals for resources. Think of the environment like a giant sieve, and only the traits that happen to fit through that sieve make it to the next generation. It's an incredibly elegant, albeit kind of ruthless, system.
In fact, the source material hits the nail on the head, stating, organisms equipped with optimal traits bypass environmental pressures, outcompete rivals, and secure higher reproduction rates. And, when we talk about outcompeting rivals, we're talking about local carrying capacity resources. The everyday stuff, like food, water, and shelter. If your physical traits let you grab that food a fraction of a second faster or hide from a predator just a little bit better, you win the right to reproduce.
Let's jump into Section 3, Hardware versus Software, the two primary engineering modes of nature.
So how exactly do organisms achieve this competitive edge in their specific biomes? Well, they use unique modifications, and you can divide these into two perfect categories. First, you've got structural adaptations. Think of this as the hardware. It's the physical anatomy configured to optimize a specific biological task. And second, you have behavioral adaptations. This is the software. These are action routines, or let's say, network protocols programmed right into the organism's operational sequence. Both are absolutely critical to the whole shebang, but they operate in totally different ways.
Let's look at the hardware first, because the structural adaptations we see in nature are honestly mind-blowing. Take desert plants. They develop waxy cuticles or needle-like leaves. That is a brilliant piece of hardware specifically designed to reduce water loss through transpiration in a harsh, arid biome. On the flip side, look at rainforest plants. They have these massive, broadleaf surfaces designed to capture low-intensity sunlight under a super dense canopy. Or how about birds? Their hollow bone architecture literally minimizes their mechanical mass, which is what allows the physics of flight to even work in the first place. It's highly specialized hardware perfectly adapted to its environment.
But hey, hardware isn't everything, right? Let's talk about the software side, those behavioral adaptations. A lone wolf might struggle to survive, but pack hunting coordination among top predators, that is a brilliant behavioral software routine that lets them secure massive food reserves. Or think about long-distance seasonal migrations. Rather than physically changing their hardware to survive an extreme weather shift, the animal's software just tells it to bypass the weather entirely by moving. Even nocturnal activity cycles, literally just waking up at night instead of the day, drastically reduces thermal stress and moisture evaporation. It's a purely behavioral shift, but it ensures survival just as effectively as a physical waxy leaf does.
Moving on to Section 4, winning the survival game. Differential survival and reproductive success.
So, we have all this impressive hardware and highly tuned software. But what is the actual end goal here? What's the whole point? Well, the ultimate evaluation of any adaptation is whether it successfully moves an individual from simply gathering resources to actually reproducing. Seriously, the most beautiful waxy leaf or the most highly coordinated pack hunting routine doesn't mean a single thing if it doesn't lead to reproduction. If an organism lives a really long time but leaves zero offspring, functionally, its unique hardware and software will just vanish from the earth. Reproduction is the singular, ultimate finish line of this natural selection field test.
And finally, Section 5, Vertical Classroom Progression, focusing on teaching competency 013A.
So, for all the educators joining us today, how do we take these massive, complex biological concepts and make them actually click for students? Teaching this concept effectively relies on a really clear vertical progression. In early childhood through second grade, you've got to keep it tactile. Focus on that visible hardware. Have your students observe physical structures directly. Get them matching different bird beaks or animal teeth to specific types of food. It builds that core foundational logic. Then, as you move into the upper grades, 3 through 6, you level up. You start guiding students to analyze how those individual structural designs actually accumulate to define an organism's entire localized niche or environmental boundary. You're basically shifting them from just looking at the hardware to understanding the entire operating system.
Which brings us to my final thought, and a bit of a challenge for you. You've seen the simulation play out. You now understand the passive filter, the hardware, and the software. So, how will you bring the dynamic, real-world energy of this field test into your own classroom? How are you going to make natural selection feel less like just another vocabulary word to memorize and more like a living, breathing puzzle for your students to solve? Definitely think about that as you design your next lesson plan. Thanks so much for joining me on this explainer. Keep asking great questions, and I will catch you next time.